All right, yeah. So, continuing the COPS experiments, Copernicus experiment devlog. So, in this one, I wanted to just try to recreate, I guess you could call it like Maya style projection mapping, or if you're coming from Unreal Engine, I think they're called decals. So basically, keeping the original UVs and then using a planar projection and getting that planar projection onto those UVs. So this was the one I thought was going to be easier than the warp projection stuff. I thought the warp projection stuff was going to be quite difficult, and this turned out to be a little bit of a brain bender. So as I did with the warp projection one, I'll probably split this up into a few chapters, but we'll see how far we get. Let's get to it. So as always, using my pig head subdivided, and then that goes out into Copernicus, which we'll see here in a second. So the main thing that happens when you do a UV projection in any package is it's basically like looking at something through a piece of glass, and whatever you can see on that piece of glass is what your UV becomes. So just like you can planar project something, you can UV project something, you can planar UV project something. It's the same process. It's kind of like how speakers and microphones are kind of the same thing. Like one takes sound and turns it into electricity, and one takes electricity and turns it into sound. So that can go either way. So the challenge becomes, like I said before, how do I use these newly generated UVs on my other UV set? And it's one line of code that the whole thing kind of hangs together on. So I'll stop yapping and we can get into it. So let's look at what actually happens so I put a normal on here, just because I usually put normals on things that I'm trying to texture because it's just useful information. And then there's this UV project node. Now, if you look on the UV project node, it says UV attribute. So if I make a new one of these, I think it'll just be UV. So I change this to UV project. So you can have multiple sets of UVs on your models. Like a lot of things use this, like Unreal Engine will use one set of UVs for the textures that you see and another set of textures for baking lighting into, right? So you can have multiple UVs. So all this is doing is it's just giving me another UV set. So if I press Shift and F5, this is the new UV map that is coming out of this object. So this is set to UV project. I can set this back to UV, and that's the standard one. So you can have as many of these UV sets. So the idea is that I need to take whatever happens in this piece of information and shove it over to this piece of information, right? So I'm basically reconfiguring the UV setup for one UV into the information of another UV, which sounds completely brain bending, and it took me a long time to really wrap my head around this. So the first thing I need is basically none of this information by default up here in the parameters page is going to go into COPS. So that was the first thing I needed to figure out, because I need to know where this thing is in space, possibly how far it is away from the surface, and then what direction it's pointing. All of that is held in here. So there's no geometric representation of this. The other thing I need to know the name of this object, because if I want to make a bunch of these and I'm explicitly referencing UV project 1, everything will look at UV project 1. I needed that to be dynamic. So those are the problems that I had to kind of get around. So the first one actually stumped me, the one that you see first. So I basically took, and there's this command called opinputpath. And this one always eluded me when I first started using Houdini. It's a lot in the simulation context, but it's not really talked about a lot. So all this does is it says, hey, give me the name of the node that's connected to my first or 0th input. So this opinputpath is what I'm putting into the name of this. So that allows me, so I'm basically taking this parameter information and jamming it onto my geometry so that I can use it later. So if I look at my geometry spreadsheet here, I have object, planar project, UV project 1. So that's the full path to this. So I can refer to this name later, okay? So the second part is, how do I get this information onto my geometry in a way that I can use it over in COPS when I rasterize it? So that's what this project data is. So if I come over here, you don't really see anything change, but if I click on this, I have all these extra parameters. So I have projection direction, which is a vector that is representing where the z-axis of my UV project node is. So basically this axis, that's that project. The hit projection is basically if you imagine the project node is like a little BB gun and it shoots out a little point and that point sticks to the pig. That's what that is. And I'll show you how I calculated all this in a minute. And then I have my projection origin, which is basically just where the center of this thing is in space. Okay, so that's what I collected. So how do I get to all of that? So it's the FOP network. So the first thing I'm doing is I'm grabbing the translation, the translation X, Y, and Z of that projection node. So so this is why I put all that stuff into a name. So I'm fetching my name attribute. And in this case, my name attribute is that node. So I'm basically wiring this into channel nodes. So this channel node, it says, hey, what node do you want me to look at? And what channel do you want me to look at? So here I'm getting, so that's that UV project node. So I'm getting TX, TY, TZ, and then I'm using a float to vector to make a position. And then I'm spitting this out as projOrigin. So now I'm encoding that position in space onto just random data that I'm putting on all my points. Now, there might be a more efficient way to do this. I could maybe do it with detail attributes, but I'm just trying to get it to work right now. Okay, so that gets my position. Because eventually what I want to do is I'll have my direction to my pig, and then I'll have my position. And so, like I said, I will array onto that point. And then I can use that point for masking. So I can mask these points so I can get the distance from that point to any point, and then I can make a mask based on this. The other reason that I want to know the direction of this is I have my normals. So a normal that's pointing directly towards that will be a value of 1. A normal pointing perpendicular to that will be a value of 0, and a normal pointing away from that will be a value of -1. So that'll also give me a directional mask. So I'll have my projection, and then if the projection is huge or I want it to fade out, I can have a fading mask from the point on the surface that the projection is on, and I can have it fade around. So this is how, if you'll see as I'm building this, if you don't have like that directional mask, your projection just goes straight through your object, right? So that's how you get into that. So this is all the stuff I uncovered while I was kind of doing this. And I was like, it really makes you appreciate well-designed software. Like it really does I mean, I'm not trying to replace Substance Painter with this. This is more of a thought experiment, but you can really see like how much like kind of like user interface has gone into this stuff to make it like look seamless in other packages, but the fact that you can do this in Houdini is still one of the coolest things I've done in computer graphics. Okay, so that gets my position. So now I can also get my rotation, but here's the rub. Rotation in computer graphics is not easy to understand. You can represent rotation in a number of different ways. The most popular is Euler rotation, right? So that's when you have your X ring and your Y ring and your Z ring, and that determines your rotation. Now, that's great for animation and people, but math does not like that. It's too much information. It's not packed efficiently. What math likes are 3x3 matrices. An Euler rotation can be represented in a 3x3 rotation matrix. They're both doing the same thing. It's like lumens and wattage, or foot-pounds and kilograms, or whatever, right? It's different ways to describe the same phenomenon. So what I need to do is take my Euler rotation that the user put in, and I need to convert that into a 3x3 matrix. So a 3x3 matrix, 0, 0, 0, 1, 0, 0, 0, 1. So this is my x-axis, this is my y-axis, and this is my z-axis. Now, if you remember, the z of my projection transformation points at the object. So I need that vector. So that's what I'm trying to get to right there. All right, so how do I do this? So first thing, just like I did with my translation, I fetch my Rx, Ry, and Rz, and then I plug that name into there so that connection is dynamic. I actually forgot to do this the first time, and I was getting really, really wacky results. So along with Euler rotation versus 3x3 matrix rotation versus quaternion rotation, there's also degrees and radians. Human beings tend to think in degrees because it's easy to understand. You have 360 degrees around a circle. Most people don't think in 2 pi r radians, like, because pi is a very abstract subject. But radians are always required for mathematics. And Houdini does not do this conversion automatically for you. So you have to put a degrees to radians after these Euler rotations. So I'm taking this Euler degree and I'm turning it into an Euler radian. So just like we did with the transformation, right? The position, we are doing with our rotation. So we're adding these, we're putting these together into a vector. So an x rotate, y rotate, z rotate. Now there's no way in Houdini to go from, at least as far as I know, to go directly from Euler rotation to a 3x3 matrix. You have to run it through what's called a quaternion. I'll explain what quaternions are later, but just know at this point, you have to turn it into a quaternion, and then you have to turn it into a matrix, right? So here, just like we did degrees to radians, we're doing Euler to quaternion. And then here, we're doing a quaternion to matrix 3. And then out of this matrix 3, we take a matrix to vector, and I pull out that z rotation, right? And then I normalize it. I don't think I have to do it because it's already normalized. And then that gives me my direction. So let me see if I can, let me try to visualize some of these. Actually, what I can do is this, I can do this. So if I take my direction, let's just plug this into my normal real quick. Let's go from here into the normal. And then if I view my normal, there we go. So they're all pointing out that way. And if I come up and I grab my rotation, you can see that they all line up with this Z. So I can press R and I can move this around. And you can see that that tracks with that. So that's how I know that that's the correct, that's the correct axis. So let's come back down to here. So that gives me my my direction. And then for my position, so let's undo this and we'll turn those. So if I take this is my projection position, and this is just to show where this is going to go. If I take my projection origin, I put that into P, we should be able to see, yeah, so that's snapping right to where that projection center is. So now how do I get that point onto my pig? That's called an array intersect, or in Houdini, just an intersect. So what I'm doing over here, I think I'm doing that. Yeah, here. So there's this intersect here. So what this takes is a quote unquote file. So you can just grab the first input, which is the geometry that we've been working on. So you can take that and put that in. You don't have to fill in group, but so ray orig is the point, like where you want this ray, the point in space you want this ray to shoot from. I have that. That's right here. That's my the origin of my projection. So I have that. And then there's ray direction. So you have your point in space and like, where do you want to point it and where do you want to shoot it? That is my Z direction. So that goes in here. So there is one thing, I tried this and tried this. I was pulling my hair out and I couldn't get it to work. So then there's like this one little note at the bottom of the documentation that says it will only pick up surface hits if the ray is longer than the distance to the surface. And so because I wasn't getting anything, because my vector was normalized, it only had a length of 1. If the projection is really far away, that's not going to reach. So just as a safety measure, I just multiplied that vector, which will just stretch it out in space. I just multiplied it by like 5 million or 50 million or something like that. So it'll always hit. So now, if that works, then I will get this. So I can check that as well here. If I come in, where's my globals? Let's cut these off. Geometry up. So if I take that and I put that in a P, and I come back out, let's just move this back. Yep, there we go. So that little point there is the point of the center of basically this vector projected down onto that. We can see that move around if I rotate this around like that. Pretty dope. Right. Cool. So now, and all that stuff is being written. Let's cut this off. All this is being written out to geometry. So this projection hit is that's being written out to my geometry, which will then be rasterized later. Let's see. Yeah. So the project direction, that's being written out. The name's already being written out. I don't really need that, but I have it if I want it. And then there's the project origin. So all this is being pushed down onto our vector-based data, which I will then take into COPS and then rasterize it and use it as I see fit. So I think that's a good spot to stop here. Like, so this is kind of like the geometry setup. And in the next lesson, we'll jump into that CopNet and look at how you can use kind of these same geometry principles when you have all that information. So it's really exciting. Yeah. So hope you're getting out of it something. Hope you're getting something out of it. Remember, everything's data, and I'll see you in the next one.